Hello, everyone. Welcome to our seminar. Today, we are very happy to have Wei-Kuo Chen from Minnesota, and he will tell us about Lévy spin glass models. Thanks, Wei-Kuo.
Okay. All right. So by the way, my Wi-Fi is a bit unstable. So in the case that it was broken, I will make sure that it reconnect really quick. Yeah.
Okay,
So
sure.
anyway, yeah. So this is based on a joint work with a student of mine and also my colleague Arnab Sen. All right. So this is about the Lévy spin glass model. It's a subject in spin glass. That has been sort of people are aware of this model, but they started in particular in mathematical context. Essentially, we have only two papers by now. One is this paper, and then another paper written by Jagnas and then his collaborator. All right. So let me tell you what this model is about. But before that, let me just recap. Let me just recap really quick what are the spin glasses. In a really rough way. So spin glasses are essentially certain alloys with unusual magnetic behavior. All right. So one of the typical example is this copper mixed with the manganese. All right. So there are many unusual magnetic behavior that we people physicists they observe in the alloys, and they want to understand what is going on, what is the mechanism behind. So you will see that somehow the model here would look like something you already seen in the easy model or something similar. All right. So one of the most important model is the so-called Sherrington Kirkpatrick. This is the Sherrington Kirkpatrick model, and the Hamiltonian is defined on the complete graph. So I'm gonna sum over all ij pairs, and then there's a random variable gij in front of the spin interaction, and I'm gonna normalize it by 1 over root n. Right. This normalization just to make sure that for each single spin, the total interaction to you will be of order 1. All right. And here, as I said, that the gij, these are IID, normal random variables. Okay, not necessarily need to be normal, but let's say following certain distribution G and centered and with the univariance. All right. So this is a model defined on a complete graph. Okay. And on the other hand, as you can easily tell, that this model is a model on a complete graph, which is very far away from the realistic model, right? So for instance, you care about the more realistic model where the spin interaction are defined according to the number of your neighbors, right? So those are the short range and more realistic model. All right. So if you look at a Sherrington Kirkpatrick model, this is really far away from what we really want. All right. So as a bridge, right, in between the mean field model and then the realistic model, people also consider the following model, which is the so-called diluted SK. All right. So this diluted SK, let me use DSK. Maybe let me use the other way instead. This model was introduced by these authors, so Vienna and Bray, in their paper, and then this model looks like the same as the SK, you again sum over all the pairs ij, and there's a random variable in front. All right, but then the main difference between this model and the SK is that I'm gonna, instead of looking at the all bounds, right, all edges, so I'm gonna look at the I'm gonna place a probability on each given edge, right, whether I want to have an interaction or not, right? So you see there's a beta, there's a Bij in front, right? So where the Bij, they are IID and Bernoulli with the rate Bernoulli gamma over n, all right? And this is independent of the G. I mean Gij. Okay. And here the of course, since I put the Poisson, I put the Bernoulli random variable in front of G, right? So you know this is essentially I mean an Heejune graph. What is an Heejune graph? All right. Okay. And one very important thing I forgot to say is that throughout the entire talk, I'm gonna focus just myself on the spin on the hypercube. Right. So sigma 1 and sigma n. This is a vector chosen from the hypercube. So for each given spin configuration, I'm gonna assign an energy according to these two Hamiltonians. All right. So right now, you know these are sort of a very important models in the field, and we want to, I mean, and then the Lévy model. What is the Lévy model? Okay, so Lévy model is, I mean, looks like almost the same as before, right? But I'm gonna let the I'm gonna let the spin interaction, the G, to be a heavy tail distribution, right? So I'm gonna let X be a heavy tail probability density. I should be more careful about my writing. This is alpha, not 2. Okay, 1 plus alpha. And then the indicator, the modulus of X is bigger than 1, and dx. And where the alpha is the important parameter in this model, and it's between 0 and 2. Okay, so be careful that you know this random variable is heavy tail, because if you look at the say the C moment of X, this guy is going to be finite if and only if that the C is less than alpha. All right, so this is really heavy tail. And all right, and then the Hamiltonian of the Lévy model is defined in terms of the Jij. So this will be written as Xij. Those are the IID copies of X divided by n to the 1 over alpha. All right. So then the Hamiltonian of the Lévy model is again sum, and then the Jij and sigma I, sigma j, and I less than j. All right. So if I put my X inside here, it looks pretty much the same as the SK, right? So here this is I less than j and Xij and sigma I, sigma j. Okay. All right. So let me just tell you two relevance about why we study this model. All right, without getting into too much detail, because I mean one of the reasons is that this model was motivated in physics paper, and then I think their explanation is way better than I can do. So I will just refer you to this paper. So this model was initiated from this nice paper, Cizeau and Bouchaud. in the 93 paper. All right. So they essentially, I mean, had a paragraph that explained pretty well that essentially the spin interaction, right? You put the heavy tail of this type is highly relevant in comparison with the what you see in the experimental spin graphs. All right. So this is one of the main reasons why we care about these a lot. All right. And on the other hand, mathematically, this is a model sort of bridge in between the mean field SK and also the Vienna Bray model, right? So just to add a sentence here. So this is SK, and this is a bridge in between the SK and then the Vienna Bray model. Right, so this is a model sitting in between. All right, we cannot see what is the model. I mean, this might be easier to see that okay, given the form is already like this, so this is pretty much like the SK, right? And the why this guy is the same as the VB, the Vienna Bray model. You will see later on that I'm gonna perform the truncation trick so that the model looks like the Vienna Bray model. So as in the usual class in the statistical physics 101, people always care about the partition function. Right? So in this case, there's no difference. So just the sum of the all Boltzmann weights. All right, and I put a parameter beta here. This is the inverse temperature. All right. On the other hand, there is also this Gibbs measure that is written as a measure according to my Boltzmann weights. All right, and I'm gonna use this notation here to mean the Gibbs exploitation. Okay, so right now here's the first main result. All right, so recall that in our model, what is the important parameter? In this model, right, the important parameter is this alpha, right, between 0 and 2, which control the tail of the distribution in the spin interaction, right? And the reason I'm gonna tell you today is that there is a major difference between alpha bigger than 1 and less than 1, right? So you can see that the behavior of the model is quite different in terms of the free energy. At least this is something that we can understand in terms of free energy. There are still many results, still many questions, I mean, widely open. Even in physics level, people don't know what to expect. All right, so this is a nice problem to invest. I mean, nice model to invest your energy. All right, so now get back to the main result. In the first case here, we will have the alpha between 1 and 2. Right, so this is the it's sort of a warm-up result, right? So I'm gonna dot the define a critical temperature beta alpha, which is the inverse of this integral. All right, here you see that there is a TH, right? TH means the hyperbolic tangent. I don't want to write tan, I mean, all the time, just TH, hyperbolic tangent. All right, then the first result is this. For any alpha between 1 and 2, and also beta less than beta critical, you will see, first of all, in the LP known, for any P less than alpha, the limiting free energy which is defined as the 1 over n and log Zn. All right. So this guy is the same as that you can bring an expectation to the log Zn. Right. So this means that you have a concentration. Right. This means you have a concentration. And in addition, you can you can right now further switch the log with the expectation, right? So this is the limits, right? So this is 1 over n and log expectation Zn, right? So this essentially means that the anneal free energy is the same as the quenched free energy, right? So you can switch the expectation with a log, right? So this is essentially due to the second moment method. All right. And finally, since we know that the last quantity here, right? The last quantity, so you know you can actually compute this guy explicitly because our Jij, right? Our Xij, they are very explicit, right? So you can handle this guy in the easier, in summer computation. And the outcome is very simple. Just the log 2 plus an integral 0 to infinity and log. And then there's a new notation. This is CH. It means hyperbolic cosine and beta x divided by x and 1 plus alpha dx. Oops. Yeah, good. All right. So this is the first main result. Okay. I have a theorem 1. This is the first of the first main result. All right. And second, I want to know the behavior of the Gibbs measure. All right. So in this case, I'm gonna consider sigma 1 and sigma 2. They are sampled, right? IID sample from my Gibbs measure. Okay. And now I want to measure how much these two vectors are similar to each other. Right. So for that purpose, one of the typical way is to look at this overlap. So that will be the average inner products of these two vectors. Right, and I'm gonna call this as the site overlap. This is the site overlap because here what is the average? Imagine that you have a graph, right? And then these I are the indices, are the vertices, right? So right now you compare the sign of the sigma 1 and sigma 2 on each single vertex, and then you look at the average. So this is the site overlap. All right, and in this case, we show that the spins are essentially uncorrelated. Right, and in this case, because the model is symmetric, if you have the uncorrelation, then this guy must be equal to 0. Right, so the overlap is concentrated at a 0. Right, so which means that essentially these spins are not, they are uncorrelated, and it looks like like a Bernoulli random variable with a 1 and -1 equal probability. It looks like that. All right, and the number 3 is a bit more interesting. I'm gonna look at the overlap on the edges. All right. So, but in this model, we have to be more careful. What do I mean by looking at the comparing the spins on the edges, right? Because this model is defined in this way, right? You look at the sum over all pairs, right? So what do you mean by an edge? apparently an age from here will mean any pair ij, right? It's trivial just from this definition, right? But it doesn't make sense if you add them. If we add all pairs ij as your age, then that will give you exactly the same overlap here. Will give you the same overlap. That doesn't make sense at all. All right. So I'm gonna look at the bound overlap on the associated to the heavy edges, right? So this is what I mean. So I'm gonna dot the k being a positive number and fixed. I'm gonna set a random number. This is essentially the number of the heavy edges, right? So what I mean by heavy, it means that the Jij has to be bigger than k. All right. So know that the Jij are IID sample from the same distribution, right? So this is nothing but a binomial random variable. And right now I have n choose too many edges, and each guy has probability, which is the minimum between the 1 and k negative alpha divided by n. Okay. And right now the m, this is a Bernoulli, right? So we know when n is getting really big, then we know asymptotically m should look like what, right? So this guy would look like the n times k negative alpha and over 2 if k is positive. All right. And on the other hand, this guy would be like of order n squared divided by 2 if k is equal to 0. All right, so here okay, so I think this should be good for now. Okay, so this is what I mean by the edges with the heavy tail, with the edges with the heavy weights. All right, and now I'm gonna define the bound overlap. Okay, the bound overlap is this. So this is Q12, and there's a normalization and sum over all pairs ij, and put an indicator Jij bigger than or equal to k, right? So I want to compare the similarities of the spins on the edges, right? So here I should put the sigma I, sigma j. This is the first spin configuration, and there is also sigma I, sigma j, and this is the second spin configuration, right? This is my bound overlap. All right, and right now the main result is this guy, the bound overlap has a different behavior with the site overlap, right? In this case, you will see that this Q12 will be concentrated at a constant alpha k alpha k to infinity and hyperbolic tangent square beta x divided by x to the 1 plus alpha and dx and square, right? This guy is equal to 0. Okay. So what it means is that this bound overlap, right? You right now look at the the average similarities of the spin configurations on the given edge with the heavy weights, right? And now you see that this quantity is concentrated at a deterministic constant. This is a deterministic constant. So essentially, what it says is that somehow, when you look at the edges associated to the heavy weights, then the edges, right, this spin interaction tend to share the same sign as the Jij, right? So from here, this is because this edge Right? So these two spin interactions on this edge, I mean, tend to share the same sign as Jij. Right? This is a rough idea why this is the case, but we should also be aware that how many heavy edges we could have in the this measure. Right? Here we have the remember this is the total number of the heavy edges. Right? So we know this is of order n, right? But in the end, I mean, you know, if you just look at a single edge, then of course they might tend to share the same. These two might tend to share the same signs to Jij. But in the meantime, you have a linearly many of them. So still, the other guys might influence how you interact with with each other, right? But the outcome is still that this guy is a positive number.
Would this statement make sense if k is like some power of n instead of a constant, or is constant the only scale that makes sense somehow?
I think the more meaningful k is the constant one. Yes, if you choose k to be super huge, then you'll be really to super heavy tail, then you know a lot energy scale, then essentially the spin configurations will be almost the near ground states.
Oh, okay.
Yeah, so then you would
Sure,
the trivial that these two will align in the same direction. Yeah.
And if k is too small, then they just won't really correlate.
Yeah.
Okay.
So if you pick k to be 0, right? K to be 0, then this guy Q12 will be like the original. It will be the R12 square. Then that will be 0.
Okay.
Yes.
Easy, thanks.
Okay. No problem. So I think this is the first main result, and this is a good time to pause here, just maybe 5 seconds in case you guys have any questions.
So all of these 1, 2, 3 are for beta smaller than beta alpha. That's the common assumption.
Yes.
Okay.
Yeah. So that is essentially the I mean that beta alpha was mentioned in this Cizeau and Bouchaud's paper. So I mentioned this paper. They conjecture that should be the high temperature regime that you see the behavior that the overlap is concentrated. Yeah.
And continue.
Sorry, go ahead.
Yeah. So and also like regarding to Mark's question, what happens if you take this k to be converting to 0 in n, like n to some negative power? Or like
if you go to 0, right? If you go to 0 too fast, then essentially you will see that the Q will be 0. Yes. I mean, you can also see from this integral that when k goes to 0, that this guy, since the integral is finite and k will be 0. Yeah. But on the other hand, if k goes to 0 too fast, this guy will look like just the R12 square. Yeah, so that you know R12 square, then you will be just this guy we know.
Okay. Could you repeat why this is the case? So when k is equal to 0, q is equal to r squared.
Oh yeah, yes. Because when k is equal to 0, that means you essentially want to correct all of the edges. Do you agree?
Yeah.
Yeah, right. So this you correct all of the edges. So here will be essentially the so here this constraint, right, indicator is not important. So you are summing essentially over all I less than j, right? So maybe I should be more careful because so when k is equal to 0, let me put it up. So when k is equal to 0, the sum, I mean the Q12, this guy should be the okay. Let me should be roughly like a 1/2. I mean, maybe let me just write this, because as I said that you do not have this constraint, right? You do not have this constraint. So the thing that you are adding here, it looks like just the R12 square divided by 2. Don't forget it's just summing over I less than j.
Oh, okay. Yeah. Thank you.
Yeah. And then this normalization outside 1/m is equal to n choose 2, right? So you know the n choose 2 cancel with the n choose 2 over here. So you see just R12 square.
Yeah, thanks.
Sure. Great. So right now I'm gonna jump into another the second result. All right. So in the second result here, I'm gonna try to understand what should be the limits. What should be the limit of the free energy? All right. So in this case, I'm gonna I'm gonna first motivate how we try to understand this. All right. So first of all, okay, I shouldn't state my theorem here. So first of all, if you look at the Jij, right, I can try to write my Jij as two components. In the first component, I'm gonna consider Jij being bigger than epsilon and Jij. And the second component is the heavy weight, so that'll be Jij. Oh, sorry, this is the heavy weights. And the first guy is the smaller weights. Okay. So the fact is that if you decompose your Hamiltonian in such a way, then this small weight here wouldn't be important in your Hamiltonian. All right. So then what you can do is that you can make a comparison with the original free energy and with the this free energy. All right, let me put expectation here since this is concentrated. So this is the sum over sigma, and then the exponential beta, and the sum, and okay, beta sum, and then the here this is just indicator Jij bigger than epsilon times Jij sigma I sigma j. All right, this is when the epsilon is small, then these two free energies, they look almost the same. All right. But on the other hand, if you look at the second component here, right? So you have this is essentially a Bernoulli random variable, and this is Jij. So you know this guy can actually be written as a Poisson, as a Bernoulli random variable B, and then the Ij times Gij. All right, this is exactly equal to this in distribution. All right, so what is B? So here B is a Bernoulli with the rate this is epsilon negative alpha divided by n. All right, and then the Gij, this is a random variable with the following density. This is alpha epsilon negative, alpha divided by 2, and indicator x bigger than or equal to epsilon divided by x 1 plus alpha. Okay, so you can really literally write this guy, right, indicator and times Jij by the products of these two independent random variables B and G, right? This is this is really equal in distribution, right? This is not approximation, right? It's a really nice nice exercise to check. You can either use the characteristic functions or just check the densities. They will match immediately. All right. So in other words, if we make this observation, now I can substitute this portion here, right, the spins interaction here, so that you see this is asymptotically like 1 over n and expectation log sigma and E beta, and then the sum of Bij and Gij sigma I sigma j. All right, so what is this? This is essentially the Vienna Bray model, right? So this is the Vienna Bray model. Okay. So this is the first important observation that we try to make a connection, right, of this Lévy model with some model that we learned already. We have a slightly better understanding, which is the Vienna-Barry model, a Bray model. Okay, but if you look at this model, somehow when you have a Bernoulli edge here, this is very hard to analyze it, at least mathematically. All right. So one of the trick is that we try to remove the Bernoulli by substituting it by the Poisson random variable. All right. So essentially, you can further rewrite. You can further rewrite this as 1 over n, an exploitation log, and E and beta, okay, from 1 to, a Poisson number. So I'm gonna put here, the upper bound is Poisson, and with a rate epsilon alpha times n. And here is going to be the same as before. This is GK, and sigma I K1, and sigma I K2. All right. So you see some new notations, right? Let me explain this just carefully. So here again, the GK has the same distribution as GIJ, right? And then the pair here, I1, IK1, and IK2, right? These two together is these are uniformly sampled from the set of indices Ij and I less than j. Right. So it's just for any given k, you sample a random vector, IK1 and IK2, and they are different, right? I less than j. All right. So this model here essentially is the Poissonian version of the Vienna-Bray model. Okay, and now let me just denote this guy by a new notation. Let me write this as right. Let me denote this guy by F and PVB, right? FPVB model. All right. So now this is a fact. All right, Penchenko, I cannot remember the exact year, but it should be 13. All right, so he proved that the limiting free energy of the Vienna-Bray model can be written as the infimum of a variational principle. There's a functional P and parameterized by the epsilon, right? So this epsilon here is the truncation level that we introduced in this truncation, right? So this epsilon is the same epsilon, all right? And this is a functional defined on certain sort of very abstract space in terms of sigma, and sigma is inside the M epsilon. All right. So let me explain what does it mean by this, right? This looks very, very neat. All right. So how to what are these sigmas? So essentially the what are sigmas? Right. Let me write here. What does sigma mean? Right, in this variational principle. So if you look at the let's say right now, if you sample a sequence of spin configurations independently, right? So you sample sigma 1, sigma 2, sigma 3, all the way from the Gibbs measure, right? And now these are ID sample from the same Gibbs measure, right? But associate, of course, to the PVB model, Poissonian Vienna-Bray model. All right. And let's assume that this guy, okay. Let's assume that this guy converges to some limiting distribution, right? So of course, you know, this is a vector, this is a sequence of vectors, right? This is an infinite sequence, and each entry here will be a n-dimensional vector, right? So when you pass to limit n tends to infinity, then you should see that this guy will go to a matrix, an infinite dimensional matrix. And let me denote this by Si and L. And IL are both bigger than or equal to 1. Okay. And the key observation is that you see in this model, because the model is mean field, right? And it's really symmetric in the sense that if you perturb the spin index I, right? You perturb the I any way you like, right? And also you perturb the L, right? Any way you prefer, then eventually you see that this limiting object will still share the same symmetry in the sense that if you perturb any finite many rows and finite many columns, then you still get the same distribution, right? So you have an exchangeability in that two coordinates, all right? So you have the this is exchangeable. All right, this is exchangeable. And if you have a matrix and it's exchangeable according to row and columns, and there's a very nice theorem due to Elders and Hoover representation. All right, so this guy, we can write this as sigma and W U WL VI and X IL. Right, so I can write this. I can express this vector, this matrix here by some function sigma, right? So here sigma is just a function, measurable function defined on this space and maps to +1 and -1. All right, and then the W, U, and Vx, right? All these notations you see here, these are uniformly sample from the 0-1 interval and IID. Right, so this is the Elders-Hoover representation. All right, so now get back to here. What does it mean by this representation? Is that this is a variational representation. In a sense, it is a variational representation in terms of the spin distributions, limiting spin distributions, right? So the sigma you see here plays the rule that somehow they arises from the limits of the spin configuration. Okay, and the function of here is not that important, right? Not that important, but let me just mention the result we have. This should be number 3. Oh, it should be okay. I think it should be number 2. All right. So the second result is the limits, right? So for any, again, alpha has to be bigger than 1 and less than 2, and for any beta positive, then you can write the limiting free energy as the infimum over all sigma inside some space n and q sigma. All right. So what are the q? What is the q here? Q sigma is the log 2 plus a functional and hyperbolic cosine times beta and the sum of a Poisson point process And the second component here is almost the same. Okay, just for completeness, let me just mention. So this cut, I mean, the CK, these are the Poisson point process, right? PPP or the mean measure mu x given by alpha dx 1 plus alpha, all right, and then the CK prime is the same, but the mean measure here is mu divided by 2. All right, and finally, you see there's a SK, right? What is SK? SK is nothing but just the sigma, and W, U, VK, XK, right? And then the SK, S1K, and S2K, they are defined in the same way. So that'll be WU, V1K, and X1K, right? So this is the variational formula that we obtain. So the way we got this is essentially coming from the, I mean, we use this representation, right? And then we analyze the limits of this PVB model when epsilon tends to 0. When epsilon tends to 0, all right? So this is the this second main result.
Can I ask a question?
Yes, go ahead.
In the PVB model, do we know if the functional has like unique minimizers in the same way that we know in like p-spin models when you're functional?
Yeah, unfortunately, not really. I mean,
okay.
Ideally, one would like to have the right-hand side being like a variational principle, sort of similar to the Parisi formula, right? And indeed, this was conjectured that the right-hand side should have something like Parisi formula. And in that case, people would call it as a Mazar-Parisi formula. The formula is more complicated, and but it's much better because you can understand the phase transition from that formula. But the drawback of this representation is that the form of the P epsilon looks like pretty much the same as the Mazar-Parisi representation. But it's just that at the current stage, we don't know how to interpret the sigma here as the functional order parameter in the Parisi's sort of formulation. So this is still still a major gap in between the Mazar-Parisi formula and this formulation.
Oh, I see. So there's not a way of there's not a clear way of taking these functions sigma and using them to describe like the law of the overlap.
Yeah, yes, no, not that easy.
Okay,
yes.
I see.
Yes.
Yeah.
Sure. Okay, so now I think I tell you the full story of the alpha between 1 and 2. And Xin, can you remind me when should I end?
I think it's usually like 45 to 50 minutes, so it's almost about time. But I think maybe you can continue for 5 to 10 minutes because I remember you have another case, right? There's a
yeah. And let me just mention the second case here really quick, just 5 minutes. Then I will done.
Okay.
Yeah.
Great.
Thank you very much.
No
okay, so the second case is the alpha between 0 and 1. All right. So in this case, somehow the limit of the free energy will have a different normalization, right? So you see here, the normalization for the free energy is 1 over n, right? It's 1 over n. And then you see a deterministic constant, all right? But for alpha less than 1, what you see is that the normalization should be n to the 1 over alpha, all right? And then it log Zn divided by n to the 1 over alpha converges to a distribution, right? So it's a convergence in distribution instead of convergence here, almost showing. Right, so let me be more precise. That the E1, E2, or this be IID exponential 1. right? And I'm gonna dot the gamma to be the accumulation of this Gaussian of this exponential. All right. And now, of course, you see you have some of this. This is essentially the arrival time. This is the inter-arrival time of a customer in the typical textbook in stochastic processes. And then the gamma j here is the arrival time of the j's customer. So this gamma j. So this is a PPP. Or this is the maybe the most basic one, right? The PPP or the units. Oops. Intensity. Right, so the unit intensity. And now by the mapping, you can right now, consider this sequence. So this is gamma, okay, so this should be gamma 1 instead. So gamma 1, gamma 2, negative 1 over alpha, so on and so forth. So this is again a PPP, right, with the intensity nu dx and equals alpha times x to the negative 1 plus alpha on this interval. Okay, now we have everything we need. Here is the theorem of today, the third theorem. So for any alpha between 0 and 1 and beta bigger than 0, the limiting free energy, right, as I said, we have to normalize it by n to the 1 over alpha and log Zn. This guy converges weakly to a series in terms of the gamma, the PPP. Right, this is the weak convergence. And somehow of course, by law of large number, right? By law of large number, since it's just a sum of IID exponential, so I know that this guy will be roughly like J, roughly like of order J as long as J is big enough, right? So I know that here it looks like you are summing what you are summing. This like you are summing the J from 1 to infinity and 1 over J to the 1 over alpha, right? So as long as your alpha is less than 1, then this is going to be a convergent series. This is a convergent series, right? But on the other hand, if you look at alpha bigger than 1, what you see, this guy will be equal to infinity. Or this guy will be equal to infinity. So you see, just to summarize that, the major difference between the alpha bigger than 1 and less than 1 is that you see a different way of convergence in terms of the free energy. All right, but to conclude the talk today, there are still many open problems open. Right, we don't know how to solve them. So for instance, the first question is that I mentioned alpha bigger than 1 and alpha less than 1, right? So of course, the next question is, how about alpha bigger equals 1? Right. So in this case, we know literally, we did not really try super hard to understand this case, right? But on the other hand, when we look over all of the proofs, and somehow this case, all of the arguments for this alpha equal to 1 case will break down. None of them will work. So somehow the treatment for alpha equals 1 is quite different from what we have in the paper. Now this is the first major question. And second question is the overlap. Right. So we mentioned the site and bump overlaps, right? In the high temperature, that the beta less than beta critical. Right, but how about beta bigger than beta critical? Right, we don't know how they should behave. Right, they should have some non-trivial distribution but we don't know. Okay, and even in this case, right here, I only mentioned a result for the free energy, but how about the overlap behavior? Right, we have zero result about this. All right, so I think it's a good time that I stop here. Thank you, guys.